Hey, welcome to another video. Today we're going to talk about one of the major attack vectors in the Web3 and the blockchain space, which is reentrancy attacks. Essentially, a reentrancy attack, if you've never heard of it, is a way of attacking a smart contract where the order of the function is not correct. So when we do functions in Solidity, for example, we tend to follow this pattern called CEI pattern, which stands for checked effects and interactions. And then when you don't follow that pattern and you swap the effects for the interactions and you swap them up, meaning the effects should always come after the interactions, but when you do the effects before the interactions, the external interactions, obviously with another smart contract, or when you're sending ether, that function immediately becomes reentrant, which means that it can get called over and over and over again. And of course, if an attacker gets hold of a function like that, it could very easily drain all the funds, for example, from a smart contract, which is what we're exactly going to look at in this video. And we're going to have a look at the code itself. I'm going to explain how the actual reentrancy attack happens. So I've got this diagram here, so hopefully you'll be able to understand it pretty neatly. And then I'll tell you how to fix the reentrancy attack. So as you can see here, we go from drain contract to balance untouched. And that is the whole goal, right? We don't want an attacker to essentially steal all of our money from our protocol. We want our money and our protocol to be safe, and we don't want hacks happening. And then I'll show you how this actually works. I've already written these examples or these contracts in Remix. So we'll just deploy them. I'm going to get rid of this little bit right here. We're going to deploy them, and I'm going to show you exactly how reentrancy happens. So without further ado, let's crack on. So like I said, reentrancy happens when you call a smart contract from inside of a function that comes from a different smart contract, or when you're sending ether. And in this case specifically, we're going to see the case of sending ether. So like I said, when we write a function in Solidity, which is the language that I'm using to write this code, we always follow the CEI pattern, which stands for checks, effects, and interactions. And like I said earlier, when interactions and effects are basically mixed up, effects should always come before interactions, but when interactions come before effects, we are going to have a reentrant function. And this is a big problem, okay? Let's actually try to understand this code a little bit. This is a contract called faulty contract. We've got a couple of errors, a mapping that maps the address of a user to the amount of the balance that is got inside of the contract, and we've called the mapping balances. Then we have got two functions inside of this contract. We've got the deposit function, which is an external payable function, and it basically updates the balance of the message.sender inside of this mapping and adds the value that the user deposits by calling the deposit function. And then we have got the withdraw function, which is the reentrant function in this smart contract. As we can see, it's an external function, and we are performing a check in here. We're getting the amount that the user has got locked up inside of this smart contract. And if the amount is equal to 0, we're going to revert with the custom error. And now here's where the function becomes reentrant, because we're performing the interaction, we're performing the external call essentially before changing the balance of the user, which is a huge mistake. And this mistake has cost millions and millions of dollars, probably billions of dollars in stolen money from protocols. So what we're doing here is we getting the message.sender and we're performing the call method on that message.sender, and essentially we are sending the amount to that message.sender. And then if it doesn't succeed, then we're going to revert with this custom error, and then we update the balance of the user to 0. Now, an attacker, could come here and create another contract. In this case, we're going to call it attacker, and we bring the external contract, the faulty contract in here, and we're going to deploy it, okay, inside of the constructor. So we're going to pass the address of the faulty smart contract. We're going to pass it into the constructor, and then we're going to have that smart contract essentially inside of this attacker smart contract. And then what the attacker is going to do is going to call this attack function, which essentially is a public payable function, and it does two things. Number one thing it does is it calls deposit, because a user must have some sort of ether inside of the faulty contract smart contract in order to be able to call the withdraw function. Because remember that if we call withdraw with the amount being 0, it's going to revert, so it's not going to go through. But in this case, we're going to deposit, or the attacker is going to deposit 1 ether inside of the faulty contract or the victim contract, and then right after that is going to call the victim.withdraw, so the withdraw function. So we first deposit, the attacker balance goes up to 1 ETH, so then we can call withdraw, this doesn't revert, and then the third thing that happens inside of this contract is that the low level call is performed, okay? And immediately it triggers the receive function, okay? And this receive function, because we're not updating the balances of the balance of the message.sender inside of the mapping, is going to continuously get called, because as long as this condition is true, so as long as the balance of the faulty contract is higher or equal to 1 ether, this receive function is going to call victim.withdraw. That's why I wrote here that it does a loop. It sort of loops over that over and over and over again, and it keeps calling withdraw, and it essentially drains the smart contract. Okay, it drains the smart contract until the attacker contract has not fully withdrawn all the ether from the smart contract. Is not going to stop. And then lastly, in the victim contract, we update the balance of the message to sender equal to 0. Okay, but in this case it's already too late because the smart contract is completely drained. Okay, so how would we fix it? Because it is really important to understand what causes the attack, but it's also very important to understand how we fix this issue so it doesn't happen. And it is really, really simple. Okay, but we're going to go again sort of line by line. This fixed contract is pretty much the same. I've just changed the effects for the interactions, and as you can see, CEI pattern checks effects interactions. We are doing it properly in here, and let's say a hacker and attacker created this smart contract again, this is the same attacker contract. The attacker is going to deposit, the attacker balance is going to go up to 1 ETH, then it's going to call the victim.withdraw, so the withdraw function here. But here's where it changes, because in this case we're going to check that the amount is not equal to 0. So if the amount is equal to 0, we're going to revert. Then we're going to update the balance of the user inside of the mapping, and because we have the amount in here, we will be able to call it down here. But in this case, we're going to update the balance of the user to 0. So now, because we've updated the balance, the attacker balance is 0 ETH. And now, if the attacker contract was to call the withdraw function again, we would run into this revert here, because now the balance of the user is equal to 0. And then once we've updated the balance of that user inside of the mapping, then we can perform the call, like the low level call, in order to basically transfer that user the amount of ether that has got locked up inside of this contract. And that's how we prevent the contract from getting drained, and that's how we keep the balance from being untouched, essentially. So it is very important to basically know or be aware that this call function will still trigger this receive function, okay? But again, this condition is probably met unless we're the only ones that have deposited into the protocol. This condition is met, but again, when we call victim.withdraw, this will run into this revert here, because the amount that the specific user calling the attack contract, the amount that he's got locked up inside of the fixed contract in this case is going to be equal to 0, because we updated it in here. So it's like we're not allowing the attacker contract to call withdraw over and over and over again. We're making it revert in here. Okay, so that is extremely important. Okay, but I cannot tell you how many scenarios have been in the past where a smart contract has been exploited in this way. So now, just so you can see it live, let me get rid of this home tab right here. I am going to, I don't even have, let me get rid of all of this transactions in here, just so it's a clear setup. Let's get rid of this. And I'm going to first deploy the faulty contract, okay? This is how reentrancy attacks happen. So you're going to see exactly what happens. I'm going to deposit, let's say 10 ether, okay? Let me change this to ether, oops, 10 ether, and we're going to transact. As you can see, the transaction was successful here, and essentially I have deposited 10 ether into the smart contract, okay? Now, I'm going to close this up. Actually, I'm going to copy the address from the smart contract, because to deploy the attacker contract, we're going to need the address of the victim, and then we're going to deploy. So, as you can see, in the balance of the faulty contract, we have got 10 ether right now. Okay, we've got 10 ether, but we're going to call the attacker, and we're going to call the attack function, which, remember, in the faulty case, it is going to call the withdraw function over and over and over again until it drains the smart contract balance, okay? So remember, we need to deposit some ether, otherwise the withdraw function will revert. And let's close that off. And now we're going to call transact, and I want you to, I'm going to zoom out, like zoom in a little bit. I want you to pay attention to what happens here, to what happens to this balance. Now you're going to call transact. Okay, good. But look, now the balance of the attacker contract has gone up to 11. Okay, that is exactly what happens. And then if we go to the balance of the faulty contract, it goes down to 0. So essentially, the attacker was able to retrieve all of the ether inside of the faulty smart contract plus the ether that he deposited. And that is a really, really bad bug. And unless you have upgradable smart contracts, yeah, you're a little bit screwed. So yeah, in this case, the attacker just drained all the balance from the faulty smart contract and got away with 11 ether. So that is the danger of essentially not following the CEI pattern in function calls, okay? Now we're going to see what happens, because I want you to see what happens when the smart contracts that we use follow this CEI pattern, okay? So I created this fixed reentrancy .sol file in here, and this contract, or the function inside of this contract, does follow the CEI pattern, okay? So checks, effects, and interactions. And we're just going to deploy this, okay? Let me just compile this to make sure it's all correct. Good. And I'm going to get rid of this deployments, get rid of the transactions too, and we're going to deploy. Why can't I see it? Oh my goodness. Okay, yeah, there you go. Fixed contract, deploy. Now we're going to deposit some ether like we did earlier. We're going to deposit 10 ether. We're going to transact, and as you can see, the balance is 10 ether. Right, now we're going to copy the address, and we're going to attempt to deploy the attacker contract, again by passing the address of the victim contract as a parameter to the constructor. We're going to deploy it, and we're going to try to call attack, okay? Just like we did earlier, I'm going to set the value to 1 ether, and we're going to transact, and boom, it failed, okay? It reverted, okay? It did not go through. It cannot be called, okay? And that essentially happens because we are indeed following the CEI pattern, okay? It's just very, 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 very important. Because if we do not follow the CEI pattern, we're going to run into this reentrancy issue, which we obviously do not want, okay? We do not want our protocol to be drained, and it is very important that you have these things in mind when you are essentially designing a protocol and writing the functions that are going to power the protocol, okay? So yeah, like I said, it's really, really, really important, okay? Awesome. So that was it, guys. I hope you enjoyed the video. I'm going to leave the code down in the video below. I also think I'm going to do like a GitHub repo with a bunch of vulnerabilities and attack vectors and potential bugs that people could run into when writing and deploying smart contracts. I'm going to create a GitHub repo, and I'll be uploading it soon to all my videos that where I talk about all these vulnerabilities in smart contracts and stuff like that. So yeah, keep an eye out for that. I will be creating that shortly. And yeah, I just hope you guys enjoyed the video. I hope you learned something. I hope this is clear now how the reentrancy attack happens inside of smart contracts, how dangerous it is. And I hope you guys have found this helpful. And I mean, hopefully it will prevent some of you from writing faulty code. So anyways, see you soon. Thank you very much for watching.